probability, and but then when you observe this one, it's like, I observe this one right here, and this one's up. The exact moment that you observe that this is up, it changes this probability field, so this one must be down at this point. Yeah, so this is like, has like huge consequences.
When you're talking about up and down, are you talking about the spin of the electron?
Yeah. So the spin states. So why, does anyone know, oh yeah.
Could you explain the spin states a little better? I took Gen Chem and I never really understood that.
Yeah, so I think we're actually going to talk a little bit about it in the chemistry lecture.
Okay.
Maybe we should save it to then, but it has, spin is actually one of the most complicated things in quantum physics. Like, spin. Like, what the hell is spin? Like, is it actually spinning? It's actually really complicated, but let's just say there's two states, up or down. But why does this differ from relativity? Or how does this differ from relativity? That's my question.
Because it says things can affect each other faster than speeds of light.
Exactly.
Over larger
So,
distances.
like relativity is like, oh, the speed of light is constant, you know, this is the fastest speed in the universe, constant in every reference frame. Well, bam, information is traveling faster than the speed of light, and information is traveling instantaneously. So Einstein was kind of like, oh my God, like, he didn't really like this, but basically what this is showing is that relativity is like limited, and quantum physics is limited, right? So there's these two worldviews right now that they're trying to put together the unified field theory, but it's still not coming together. This is basically one of the things that's showing, like, really, really definitively, like, quantum physics has different properties than relativity. So, yeah.
Like Einstein wrote a whole paper on like the paradox, like called the EPR paradox,
Yeah.
about like entanglement and stuff.
Mm-hmm.
You guys should look that up.
This is the EPR
Yeah.
test, yeah.
So this might be on something totally different, but just to gain an understanding, when I took a class, Ways of Knowing, we talked about this man who did an experiment where he took a sample of his semen and left it in a lab in LA, and then he flew to Arizona and recorded all of his emotional feelings, like whenever he changed emotions, he recorded that, and then when he got back to his lab in down south somewhere near LA, he looked at the sample of semen and how it had changed, and it correlated exactly to his emotional change in state. Is that similar to that, or is that something totally different?
There's also other experimental evidence, like stuff like that, where they took like a swab in someone's mouth, a cell culture, and then when they're in different states, the biophysical characteristics change as their emotions faster than speed.
Yeah,
right?
It was instant.
But that doesn't necessarily come from quantum entanglement. I do think that there's interesting phenomena there to be researched, but quantum entanglement only occurs at a scale which is really, really small, and at an energy scale which is really, really small. This basically shows that like quantum entanglement in neurons is kind of like physically impossible because they're too large. Quantum entanglement within biological systems is physically impossible because they're too large. But biological systems might have entanglement phenomenon. That's not saying that it's quantum entanglement. It may be something else. But quantum entanglement doesn't describe that. But there may be a need for a new theory to describe that.
So, you know, why do we need a unifying theory? Why can't we just say, well, this is the way that little things act quantumly and big things act on this rule called general relativity? And this is just how, this is our theory, that little things act like this and big things act like this.
Oh, why do we need a universal field theory?
Yeah,
I think it's like an assumption by a lot of physicists that they're trying to strive for that. When you look at a lot of the equations, like say electrodynamics, it's like all these crazy phenomena of electrodynamics, electromagnetic waves, magnets, current generators. It's like, oh my God. They're all described by 4 equations, 4 Maxwell equations. Everything comes out at 4 Maxwell equations. And then Einstein's like, look, all those 4 Maxwell equations come out of one relationship. And so it's like, and it's really related to like vector calculus and stuff. It's like there's mathematical symmetries, and like it's really amazing how they all like kind of interconnect and they come from an individual source. And then like currently in quantum physics, like they've kind of unified 3 of the forces, or 3 of the 4 forces within nature, like the strong force, the like within protons and stuff, the weak force like radioactive, electromagnetic, and then gravity is like this other thing. So like they've already combined 3 of them into one theory, but this one is like outlying. So it's just like it's just an assumption. It doesn't need to be true. this idea of a unified field is not necessary. And it kind of like talking about the limitations of our, like, why are we even thinking of like this anyways? You know, like, of course our mental map's going to be limited. We're never going to describe it perfectly. So talking a little bit about cosmology, so this is basically now, when Einstein applied his theory of relativity to accelerating bodies to non-inertial reference frames where things are changing, he basically discovered the essence of gravity, which is a really cool outcome. Dude, Einstein was so cool. Like, he came up with the photon. He won the Nobel Prize, the photoelectric effect, special relativity, and general relativity, and the EPR stuff. Like, come on, this guy was pretty smart, right? So, like, basically, within four-dimensional space, there can be different curvature, and that's like related to the curving of space and time, which is like gravity. So, like, if you have like a sheet of paper, like this would be like a flat surface. Like, and this is a two-dimensional analogy of something like three-dimensional, or four-dimensional, by the way. So, like, if this is a 2D paper, you can draw a little triangle. Okay, all the angles equal 180 degrees, right? But then if it's on a sphere, it's like, oh, I can still draw a triangle, but now all of a sudden, the angles are bigger than 180 degrees, which is like against Euclidean geometry, right? This is like non-Euclidean geometry. Or hyperbolic space where it's curved inwards and the angles are smaller. So basically, like, what does this mean, right? So like, okay, you know when you ever been like in an airport and you look at those like airport maps and then you see like, oh, it's like United States to Europe and it's like this crazy arced path. You know what I'm talking about? Where it's like those airplane like diagrams where it's like, here's how you get to here, here's how you get to here, and they're all like curved paths. And it's like, why aren't those straight? Does anyone not know what I'm talking about? Okay. So it's like, why aren't those straight? Yeah.
Because the Earth is turning as the plane is flying, so you wouldn't be going really in a straight line if you tried to make a straight line.
I think it's something a little
more.
Turning is part of it, but there's another.
Okay. That's what I know.
That's what I learned in
Turn.
Yeah, because when you're in the air, the Earth is spinning underneath you.
And it's curved too.
Yeah, and the Earth is curved.
Yeah.
So you do the curve to account for that.
It'd be a lot longer if you just went in a straight line.
Yeah.
It'd be like, it's super shorter because it's like.
Yeah. So due to the curvature that things are like curving. So they're moving in a straight line through the curved space, but in our lower projection of it, it looks curved. So actually everything is moving in straight lines through 4 dimensions. But our planet, like, you know, we're like, oh, the planets are circling the sun. They're moving in a straight line through 4-dimensional space, but to us in 3-dimensional space, it looks like they're spinning around. So all of gravity is based on this higher dimensional curvature. It's pretty hard to like visualize and understand it, unless you're like on some stuff. But basically, like, just think about it like this, right? And black holes are like the craziest thing. It's like, this is based, okay, there's something that's also really important that I forgot to mention. So basically, yeah, right here. More curvature equals more contracted space and time. So like, basically like, okay, if this is a black hole, right? When I'm right here, a clock is gonna be moving faster than when a clock is right here. A clock's gonna be moving much slower. So when there's a more gravitational field, time's moving slower, right? So, okay, when I throw an object, like, let's say it is in space, there's no gravity, and I throw an object, it's gonna wanna go from point A to point B in the shortest amount of time. It's gonna go, things move in a straight line because it goes the farthest distance in the shortest amount of time. But guess what? If this is slowing down time, it can go like, let's say it can go point A to point B in this amount of time, or in the same amount of time, it can go from point A to point B. Because if it's moving downwards, time is moving slower. So things are trying to always optimize their movement through space and time. And when time is slowing down, they curve. And this can also be explained through higher dimensional analogies too. And then at a black hole is basically at the point where time stops. So like, if a clock is going, like at the black hole radius is defined when the speed of light can't escape. So like, basically time like stops at that point. That's kind of like, this is maybe, a lot of times people use like the rubber on a sheet analogy. It's like, okay, I have this like big bowling ball on this like sheet, and then when I throw around a little like golf ball, the golf ball's gonna roll around the big thing, right? And then like as it gets to the bottom, it'll roll faster or something, or if you throw it, it'll kind of curve. But that's kind of like a bad analogy because it's a three-dimensional thing, right? So it can go, it's not a curved sheet, it's like a curved hyperspace. Yeah, so here's just talking a little bit about the timeline of the universe. So the Big Bang, this is like the theory, inflation period of time, and then all the galaxies formed, and the separation of everything. And then here's something interesting. So here's like what our time, and then when we look backwards out into the universe, we can see this thing, the cosmic background radiation. And this is kind of like an image of the first like energy distribution in time. Interestingly, like when looking back and like looking at the distribution of galaxies, like we can see that light is curved because like matter like creates gravity which curves light. And interestingly, like the amount of light that's being curved is way, way more than the amount of mass in the universe. So right now, this is like our energy distribution, like understanding of the universe. That only 4% of it is normal matter, and that 21% is dark matter, and that 75% is dark energy. So this is saying that everything that we observe is only 4% of matter, and that there's really this other thing that we don't know what it is, but like we can see that it affects like the curvature of light, like dark matter, and then dark energy is like the force that's like ripping everything apart. Like gravity like brings everything together, so why is everything going apart? Shouldn't everything be coming together, right? Well, it's because this dark energy is accelerating space and time, and like it's kind of like it's like a bread with raisins in it, and it's expanding, and everything is expanding from each other.
Hey David, so correct me if I'm wrong, but I remember one of the ways they discovered dark matter and dark energy is they said, okay, here's these planets, and these planets are going around these stars, and it's very predictable in this way that we know it's